Assalamu alaikum. This is the lecture 3 of machine learning, which will comprise on the discussion of nearest neighbors algorithm and Tussian trees. So as with the previous lecture, we have some fundamental concepts about supervised learning, and we are going to continue our discussion with the same concept. However, this time we are going to use the examples of image classification for both of our desired tasks. So after some fundamental discussion about some new concepts in the supervised machine learning, we will discuss our first classifier, which is named as nearest neighbor classifier. After the discussion and the implementation steps of the nearest neighbor classifier, I will discuss some pitfalls of this algorithm, that what are the difficulties to manage classifying examples using the nearest neighbor algorithm. And in the top of that, in the final discussion of the nearest neighbor, I will present a demo and some examples of the nearest neighbors classifiers. Then we will move our discussion to the decision trees, and we will look how we can construct different decision trees to build classifiers for decision making. And there will be some discussion about information theory and specifically quantifying uncertainty, and there will be two concepts from information theory, for example entropy and information gain, will be discussed in the decision tree algorithm. So let's recall our first definition of the supervised learning. In the supervised learning, we had the task to learn from the examples to imitate a function that is dependent on the input data and it results some output labels. So the task of the supervised learning is to learn a function that accurately predicts the data to the target value. So here we use the training examples, and learning algorithm is given the correct value of the function for particular inputs. These inputs are the training example. So our goal is to find a hypothesis or a function that correctly maps the inputs to the outputs. So we will look into the measures that will measure the approximate mapping of the input to the outputs. So before moving forward, let's have some discussion about the performance measures. How you are going to measure the performance of your classifier, or in other words, how you are going to say that your algorithm or your classifier has performed at a certain level. So evaluation of a classifier is often significantly trickier than evaluating the regressor, because in the classifier you have to match the exact class value. However, in the regressor you have to match an expected value, which can be a continuous value. So therefore, a slight mistake will not produce a significant effect towards the error. However, in the classification, if you slightly miss the target, your classifier will result in higher amount of error. So there are many performance measures available, and one of the common is to use the accuracy performance measure. In the accuracy, the machine learning is typically performed on a task. As we described the definition of machine learning in the first lecture, the machine learns with the experience E, which is based on the training data, and it measures its performance with some performance criteria which is specified by P, and it had to be defined. For example, you can use the ratio of correctly classified examples with respect to the total examples. So this particular performance measure is called the accuracy, and it is often used in the classification task. For example, you had the 100 examples and your classifier can correctly classify the 70 of 100 examples. Therefore, your classifier may have the accuracy of 70%. So another important term in performance measure is the confusion matrix, which is a much better way to evaluate the performance of a classifier. In this way, you construct a confusion matrix. The general idea is to count the number of times instances of class A are classified as class B. So in other words, you count the correct examples and the incorrect examples, incorrect targets. So each row in the confusion matrix represents the actual class, while each column represents a predicted class. So if you take the binary classifier, you can construct a matrix for a binary classifier while representing the each row in the confusion matrix as the actual class. So for the binary classifiers, we had the positive and the negative class. So the rows represent the actual classes while the column represents the predicted classes. So you can mark the predicted class as positive and negative. So you may get four values in two way or the binary classifier. So positive examples which are predicted as positive are the correct examples. On the same hand, negative examples predicted as the negative examples are the correct output. On the other hand, positive examples which are predicted as negative are the errors, and the negative examples predicted as positive are also counted as errors. So you get a diagonal of correct predictions and another diagonal of incorrect predictions. So for a multi-class problem, you can augment the confusion matrix to have multiple rows and multiple columns exactly like the binary classifier. So the confusion matrix gives you a lot of information, but sometimes you may prefer to use a more concise metric, and precision is one of the metrics which is more precise than the accuracy. So an interesting one is to look at the accuracy of the positive prediction, and this is called the precision of the classifier. So if you take the example of the binary classifier presented in the previous slide, we had the positive examples and the negative examples. We had the positive class and the negative class. So the examples which were predicted as which were actually positive and predicted as positive are termed as true positive. On the other hand, the examples predicted as negative and they were actually negatives are called true negative. So these are the correct predictions. On the other hand, if the actual class is positive and the predicted class is negative, this is the false negative. That means the class was positive but it was falsely classified as negative. On the other hand, if the actual class is negative and the classifier predicts it as positive, it is called false positive. That means the class was negative but the classifier falsely predicted as positive. So the precision is the measure of true positive over the whole positive predictions. That means true positive over true positive plus false positive. On the other hand, there is another criteria to measure. A trivial way to have the perfect precision is to make one single positive prediction and ensure it is correct. So if we have one positive prediction and no false positives, we can say that our precision is 100%. But this would not be a very useful criteria since the classifiers would ignore all but one positive instance. So precision is typically used along with another metric named recall, also called the sensitivity of the true positive rate. This is the ratio of positive instances that are correctly detected by the classifier. So it is the ratio of the true positive over true positive and false negatives. So these are the two important criteria or performance measures which are quite widely used in the machine learning algorithm performance evaluation. So I think this rudimentary information will be enough to capture the concepts of this lecture. So we take the example of the image classification for this particular task or this particular algorithm. So image classification is a core task in computer vision, and machine learning algorithms need to handle a lots of types of data. So machine learning algorithm can be fed with the images, textual information, audio waveforms, credit card transaction, etc. But for this case, we take the example of images. So for example, we came across a famous application which is a cat image classifier. So assume you have given a set of discrete labels and you have to identify cats from the images. So you may have number of different animals and you want to classify class of each animal. So if you apply simple classification task on this image, we can clearly say that it is a cat. But if you apply the image classification task, image classification may use the probabilities to predict the output of this class. And for example, a typical classifier takes this image as an input and predicts number of probabilities for each of the labels. For example, the classifier is 82% sure about the image that it is of the cat. However, there are slight chance that it can be a dog due to its resemblance of pixels with the dog. So, as you can see, we are sure about it that it is a cat. However, algorithm is slightly cautious of the resemblance with the dog. So how we are able to distinguish this image from the dog? Because we have been seeing a lot of cats since we have seen the first cat. So we have the higher probability that this image is from the cat. On the other hand, if you take the problem to the machine learning, there is a significant semantic gap because we observe the patterns by visual information. However, the computer observes the patterns using the represented 3D arrays of numbers with integers between 0 to 255, specifically for the images. So for example, we have the image of the dimensions 300 by 100, and for each image we have three channels for red, green, blue, so each pixel will be multiplied by 3. So there is a common strategy that helps us to represent this input as an input vector. So this helps the mapping to another space that is easy to manipulate by the computers, and this space is often represented in vectors. Therefore, vectors are a great representation since we can perform the linear algebraic expressions and operations on vectors. So whenever you are dealing with the image classification task, you will convert the image to some kind of vectorized form. So you can use the raw pixels. For example, you can convert the actual images into the pixels, or you can convert the images to the vectors. So what is the benefit of converting the images to the vectors is that you can do much better if you have to compute a vector of meaningful information. That means you take the most significant pixels and eliminate the pixels which do not contribute in prediction of a particular class. However, there are other significant challenges in the prediction of image classification because there are a lot of variations from the images. For example, you may capture the image from the different angle. Therefore, this will result in the viewpoint variation. So from the different angle, a cat may look like from the different perspective, and it may be different in each picture. So you have to have the significant input value so that your classifier can learn the different perspectives or viewpoints of the same picture or same animal. Similarly, you may have the effect of illumination where you can have the lights or the darkness of the images or other shades which are expressive in many forms, but they are different from each variation. And there are a lot of filters in current um, advent of uh, image sharing websites, and people put a lot of filters on the images of animals, and it is also a challenge for the image classifier to read those altered values with different kinds of illumination. And additionally, you can also face the challenge of deformation. As you can see, a cat may be sitting in a different formation or standing in different formation. Additional challenges also include the background clutter. For example, your image or your classification task may resemble with the background noise, or your images are occluded with some kind of other material, as in this case the cat is hidden between different elements or equipments. You may have the intra-class variation as well, so that the in the same class you may have the different species or different variations of the classification task. So you have to deal with a number of challenges to construct a significantly voluminous dataset so that your classifier can learn better and predict better. So this is the actual data-driven approach. So image classification is unlike some simple task or some repetitive task such as sorting a list of numbers, and there is no obvious way to hard code the algorithm for recognizing a cat or other classes. Therefore, you will put the emphasis on the collection of a dataset of images and labels, and you will try to overcome all the challenges that we have discussed in previous few slides. So then you use the machine learning algorithm to train on that data for an image classifier, and then evaluate the classifier with a withheld set of test images. So you train using the train images and the train labels, and this will return a model, and you can use that model to predict on the test images, and then you use the performance measures described in the previous slides along with the other performance measures which we will discuss in some other lectures depending upon their need of usage. So your example training set may consist of a different training examples for each class and different labels for each class type. So in this case, our first classifier is the nearest neighbors algorithm. So suppose we are given a novel input of vector specified as x and we would like to classify it. So in simple terms or in the image classification terms, we are given an input image of a cat or another uh, animal and we would like to classify it or label it. The idea of the nearest neighbor algorithm suggests that we should find the nearest input vector to this example in the training set and copy its label. That means we should match the image of the cat or other animal with the other training set that we have remembered or we have in our memory, so we can compare those images and we can find out the least differences and then assign the values with that class. So in this case, our input is the training set T and the example we want to classify. And the task we have is to determine the class of the input example. So this is the procedure. In the training set, you find the examples and then find out the most similar example to this example and determine the class of that similar example and label current example with that class. So for example, we look into our um, imagine imaginary database of cat images and we see that our picture resembles with the cat and we label our picture with the cat. So this is the simple algorithm of the nearest neighbor classifier, which says that you find the examples and the target labels from the stored training set, which is closest to this example. That is, you have the minimum distance of those two examples. So then you output this example with the label of the most relevant or most near example. So that is the name suggests nearest neighbor classifier. What does it mean from the word similar or the nearest? So you can find out the similarity or the nearestness by the calculation of the distance between two examples. So for example, if you have discrete attributes, you can find out the number of differences, between the features. And on the other hand, if the attributes are numeric, you can calculate the geometric distance. So greater the distance indicates that lower the similarity. So here is a typical example or a typical uh, distance calculation formula in which you calculate the distance from two attributes or two values of x and y and you find out by taking the square root. There are other alternatives which we will discuss briefly. So let's take the simple example we have been discussing from the lecture 1, which is the Johnny liking the pie. So again we have our training set T with the 12 label example and we are encountered with a new example and we want to predict the class of this example. So as our algorithm suggests that we need to find out the differences between each of the feature attribute and then calculate the total number of differences which are listed in this column. So as you can see, we compared the example with all the training set and we listed the number of differences, and in this case we have listed 3, 4, 4, 4 up to so on number of differences. So as you can see, here is the example 5 which has the least amount of differences. Therefore, this example is similar or nearest to the example 5, and our algorithm suggests that if you find the nearest example, copy the label to this example. Therefore, this example will be labeled as positive. So in the previous example, you counted the number of differences. However, you can formalize the nearest in terms of Euclidean distance as well. So here is the formula to calculate the distance between two points or two examples. So this is the working of the Euclidean formula described in the previous example. So we have one example to classify, which is provided with the three attributes 2, 4, 2, and we want to predict the output. So we have four examples and we calculate the Euclidean distance of this example with the each training set example, and we can find out the least amount of distance. So we can see that this example is more near to a positive example again. So as we have seen, there are multiple ways to calculate the differences. And there is a problem: if you use different metric, it will identify a different nearest neighbor, and there is a possibility that a different class label will be predicted because different formulas will result in a different value, and you may have distortion of labels in terms of the implying formula or the metric to calculate distances. Therefore, the distance metric has to be tailored to the concrete classification problem. And there are many distance metrics are proposed, and all must satisfy the following axiom. So we denote the distance between 2 points x and y as d of x comma y. So we must be sure that if we want to calculate the distance with the same example, the distance should be equal to 0. And we are also certain that the distance between two examples will always be greater than 0 because there will be no negative distances. And the distance between 2 points, for example, distance between x and y will be equivalent to distance between y and x. On the other hand, distance between two uh, consecutive points, for example, distance between x and y, and the distance between y and z will always be greater or equal to distance between x and z. There is no chance that the distance will be less than the accumulative distance. So nearest neighbor also define Decian boundaries, the boundary between the region of input space assigned to different categories. So for example, these nearest neighbors are classified as positive examples and the red dots are classified as the negative examples, and the boundary between the regions of these input space is assigned to specify the distance between different classifications or different categories. So as an example, you take the dataset of CFAR 10, which has 10 labels, and it has 50,000 training images and 10,000 test images. So here are the label examples or target labels, and you can use an image classification algorithm to classify on these training data, which is 50,000 training images. And for every test image, the examples of nearest neighbors are in rows. For example, in the first case, we have the example of horse, and there are different horse images which are close to the horse symbol. And you can see there are other symbols as well, other images as well, which are not horse, but these are equivalent to our horse image. Therefore, most nearest image will be marked as the output label. So you can look at so you can look online for this particular uh, example dataset, and you can use the nearest neighbor algorithm to classify and check the accuracy and recall measures of this dataset for the nearest neighbors algorithm. As you have seen in the previous slide, for every test image you find the nearest train image with the distance minimum to that training example, and then predict the label of the nearest training image. So for this case we choose a different kind of parameters or different kind of distance formula. For example, for level 1 classification task, you can use the Manhattan distance. For example, you can simply calculate the distance or absolute value of the distance between the 2 points. Or you can use the level 2 Euclidean distance, in which you take the square and then sum all the distances and take the square root of the values. So here is an important definition. So any parameter you choose is the choice of the distance, and it is called the hyperparameter. Hyperparameter is used by the algorithms to specify the actual working or the optimization of the algorithm. Hyperparameter is the parameter of the learning algorithm, not the model. It is not affected by the learning algorithm. It must be set prior to the training, and it should and must remain constant during the training. The amount of regularization to apply during the learning can be controlled by this hyperparameter. So different learning algorithms have different hyperparameters, and we will discuss each kind of hyperparameters with the implementation of each learning algorithm. At this point, you should ask a question that the nearest neighbor algorithm should fall into a trap, that if the distance from the current predictable example is close to a wrongly classified example, then the algorithm may wrongly classify the predictable example. Therefore, the algorithm has the problem of the noise, and there are two types of noise. First is the class label noise, and the second one is attribute noise. For example, you may have the training set which the class provided for an example is incorrect. For example, in the training set, you may have the image of a cat which is wrongly labeled as dog. And when you compare the new example, which is closely linked to that cat, but the label is the dog, so you classify that example to the dog. The second kind of noise problem is the attribute noise. An attribute's value is incorrect. Therefore, the nearest neighbor may not be really the nearest one. For example, there may be some hindrance or occlusion so that your cat image is not correctly readable, and it may be close to or wrongly classified example. Therefore, you may classify the cat as another animal. So, to overcome these slightly non-trivial problems, you can use the multiple neighbors, or instead of the one nearest neighbor, you can employ the usage of k nearest neighbor, and the algorithm is the same, but you just replace the nearness property with the multiple neighbors. The main benefit is that you can use the voting classifier to overcome the noise. So you first find the k nearest neighbor. It can be 1, 2, 3, 4, 5, up to so on, depending upon the need of the task. So you find those k nearest examples. Then for all those examples, you have them vote on the label, and the maximum, the class with getting maximum votes will be the class of the example. For example, you can have the data and you employ the nearest neighbors algorithm, and your prediction may look like this. However, if you use the 5 nearest neighbors classification, you can see you can clearly differentiate the boundaries of different examples. So as an example, you can see we have a one nearest neighbor example, and we may get a noisy sample as marked in the blue shaded circle. So every example in the blue shaded circle will be misclassified as the blue class because the nearest neighbor of this class will be the blue class. Therefore, you will be bound to classify that example as the blue based on the nearest neighbor assumption. However, if you employ the voting classifier here and you pick three nearest neighbor, that means you will find out the three nearest example. For example, we can say example 1, example 2, and example 3, and then let those examples vote for the third example. For example, for the predictable example. For example, we are classifying again another example which is also in the shaded area, and we want to classify the example, and we ask for the votes of the three nearest neighbors. So as you can see, we have only one blue label and two orange labels. Therefore, we have two votes for the orange and one vote for the blue. Therefore, the examples in this area will be classified as orange labels. This leads to the question that what should be the value of k? How many neighbors should be employed to vote on a specific example? So you can use different values. Therefore, you have to trade off between the values to choose the k. So if you use a smaller value of the k, for example, if you use 2 or 3 or up to 4 neighbors, you have the chance to capture the fine-grained patterns. That means you have the chance to identify the least dissimilarities between the examples. However, this may overfit, particularly because due to noise, your algorithm may overfit the data during the training, and it may not behave well in the testing. Therefore, it may be it may get sensitive to the random idiosyncrasies in the training data. On the other hand, if you use the large K, it makes a stable prediction by averaging over lots of examples, but it may underfit because it may fail to capture the important irregularities. For example, it may, if you use a large value of the K for the image classifier task we are discussing, it may classify the dogs and the cats in the same class. So as a rule of thumb, you should use the K it should be less than square root of the number of examples. So if you have the number of examples known, you calculate the square root and you should employ the number of k always less than that value. So this diagram represents the error rate, which the impact of k or the number of voting classifiers or voting neighbors have on the training set. So as you can see, if you increase the k, the error rate decreases to a significant portion. But if you keep increasing the value of the k, the error rate may gradually tend to rise. Therefore, you have to choose an error rate, the value of the k where there is a little chance of the error rate. So we may choose the value of k for this particular task at here. So do you think that the voting can solve all the problems associated with the nearest neighbor classifier? Well, this may not be the case. And should more distant neighbors be given the same vote? I think not. So in this picture, you can see that we have a 5 nearest neighbor classifier and it will label the examples as negative, but it should be positive. So we have example this here and we can see that if we employ the 5 nearest neighbors, we can see that the two nearest neighbors are positive and three nearest neighbors are negative. Therefore, this example will be classified as negative. However, this is wrong because this is more close to the positive example. So what you can do? So one way is to give the priorities to nearest examples, the examples which are nearer to the uh, predictable example has the more power to vote or more weight to have the outcome on the prediction. So in this way you can employ a weighted k nearest neighbors principle. So you can calculate the distance of each point or each example with the participating classifier examples. So you assign the distance of each example with the d of I, and df1 is the training example nearest to the example x and dfk is the example most distance from the example x. So if we have an example here and we have 5 examples around it, so df1 is the distance of the nearest example and the df5 is the distance, so dfk is the distance from the most distant example. So to calculate the weighted k nearest neighbor, the individual nearest neighbor get the following weights. So you find out the distance of each value. Uh, you you subtract the distance of the maximum value to the each value and then to divide the subtracted value from the distance to the least value. So you do it for all the example except if it is the same example. So for the classifying this example x, find the k nearest neighbors of this example, calculate the weights for each nearest neighbor, and then calculate the values of positive weights and the negative weights. And then if the positive weights are greater than the negative weights, label the example as positive, otherwise label it as negative. So this is an illustration of weighted k nearest neighbor. The task is to use the 5 nearest neighbor classifier, which is weighted, and to determine the class of the object x. So we denoted the distance between x and the 5 nearest neighbors as d1 to d5. So since the minimum distance is d1 and the maximum distance is d5, then the individual weights are calculated as follows: that differentiate the you take the difference of the each example from the largest distance and then calculate the result for each example. So we can see we can find out the 8 minus distance of each example divided by sine 7. So this gives us the values for each neighbor. For example, for the weight 1 we get 1, for 2 we have 5.7, for 3 we have 4.7, for 4 we have 3.7, and for 5 we have 0. So in for this particular example, we had two nearest neighbors which are positive and the remaining three are negative. So we summed up the values and classified the x example as positive because sum of the two positive values was greater than the sum of the three negative neighbors. There is a final problem with the classification task of the nearest neighbors, that there are some dangerous examples, the examples which lie on the borders or the decision boundaries. So it is difficult to classify these examples in any algorithm. Therefore, you can use the different techniques to eliminate this kind of error. As you can see, there is a mixture here, that some examples are positive which are closely related to the negative examples. So one of the techniques to overcome this problem is to employ atomic links. Atomic link is a pair of examples of two examples x and y satisfying the following three conditions. So we find out the true examples x and y, which are the nearest neighbors of each other. So we can say that x is the nearest neighbor of the y and y is the nearest neighbor of x, but both have different labels. So as you can see here, we have positive and negative examples. Here we have positive and negative examples, or in this case we have positive and the negative examples. So both are the nearest to each other and both have the different symbols. So these are the lines which indicate the atomic links. Once you have identified these atomic links, you should remove these borderline examples which participate in these atomic links. So this will greatly reduce the problems with the borderline values. So that is the working of the nearest neighbor algorithm or the k nearest neighbor algorithm. However, there are some general problems or pitfalls for the nearest neighbors algorithm which you should keep in mind whenever applying the nearest neighbors algorithm to any dataset. Especially in high dimensions, the k nearest neighbor suffers from the curse of dimensionality, because as the number of dimensions or the number of features increase, you have to calculate the distances for the predictable example with each feature of the training set. Therefore, KNN may suffer with the increasing dimensionality. Another perspective of the curse of dimensionality in high dimension is that most points are approximately at the same distance in the high dimensions, but they are away from the lower dimensions. So this is one example of how two-dimensional visualization of high-dimensional spaces can be an extremely misleading, because in the high dimension the images or the examples may be spread across different dimensions. But if you transform those examples into a low dimension, which may look that the examples are quite similar or close to each other. Therefore, KNN does not suit for the um, for the examples which have very high dimensionality. Another problem is to deal with the irrelevant attributes. Remember, you are calculating the differences or distances between the attributes, and there are some irrelevant attributes which will contribute toward the increase of the distances. However, these attributes do not affect the class, therefore these attributes should also be eliminated. For example, in the picture below, the example 1 is positive and yet its nearest neighbors are negative. So in pure nearest neighbors philosophy, it should be classified as negative example. But this may be a result due to the calculation of irrelevant attributes, and if we remove the irrelevant attributes, we may have the chance that this example may be placed here. Another problem that k-nearest neighbor suffers is the problem of scaling. The nearest neighbor will change if the temperature is in the centigrade instead of the Fahrenheit. For example, if you use two different scaling parameters for two different features, the distances between the examples may vary. So as you can see, there are two examples and we have used the centigrade and the Fahrenheit scaling. So as you can see, if we employed the centigrade mechanism, we can see the example 1 is greater than the example 2. The distance between the example is closer to the example 2. Therefore, the example should be labeled as negative. However, if you use the Fahrenheit distance measure, you can see example 1 is less than example 2. Therefore, example will be marked as positive. So therefore, you have to use the same scaling for each attribute or feature vector. So nearest neighbors can be sensitive to the range of different features as well. So one attribute can overwhelm others because if suppose you have one attribute x1 which has the range from 0 to 1, and when you calculate the differences, this will contribute very slightly towards the actual distance. However, if you have another parameter which ranges from 0 to 100, and it will significantly contribute towards the actual distance calculation. So you may have also the problem of mixtures of Boolean and numeric attributes, and it is difficult to calculate the different values for the numeric and Boolean attributes. So how will you able to classify that the difference between summer and the winter is greater than the distance between 0.2 and 0.9? Therefore, you have to use the same scaling for the nearest neighbors. Also, in the discrete values, it is the difference between the summer and the winter is greater than the distance between the summer and the fall. So you have to use some ordinal values to overcome these scaling problems. One of the simple tricks is to normalize the values which have the different scales using the zero mean and unit variance, and then you can compute the mean and the standard deviation using these formulas. So, or you can make sure that each attribute falls into the unit interval between 0 to 1. So there are different mechanisms to convert the Boolean and numeric attributes to this kind of interval. Or even discrete attributes can be um, replaced using the ordinal encoders. In the final pitfall that the nearest neighbor algorithm suffers from the computational cost. However, you may be surprised to know that there is zero training time for these nearest neighbor algorithm, because you do not have to learn these examples before calculating the label of a new training example. So whenever you want to classify a new example, you have to perform number of computation at test time per query. Therefore, it is also similar to the naive algorithm discussed in the previous lecture. So you calculate the d-dimensional Euclidean distances with n data points, which has the computation cost of big O of n multiplied by the dimension. Then you have to sort these distances to find out the minimum distances, which have also the computational cost of big O of n log n. So this is quite computational cost. So this must be done for each query, which is very expensive by the standards of learning algorithms. And if you have million of examples, for each million of examples, you have to repeat this step. So you need to store the entire dataset into the memory, which is also problematic if you have the memory restrictions. However, tons of work has been gone into this algorithm, and the data structure for efficient nearest neighbors with a high dimension and large dataset is possible, and you should find the alternate sources to explore further about these um, limitations. So if you compare the nearest neighbor algorithm with the naive Bayes, it is closely linked with the naive Bayes algorithm, which have the same number of training errors. However, the training error of the nearest neighbor is slightly greater at the start of the learning phase or comparison phase, then it normalizes to the Bayesian network, so they may have almost equivalent performance on the training sets. So here is a link to the demo. You should open this link and explore the working of the nearest neighbors algorithm, and you should change the parameters to have different nearest neighbors and different training values. Here is an interesting example of the nearest neighbors algorithm, and the authors of this paper have referred this example as where in the word. So this is a nearest neighbor recognition example. So in this example, you provide an image to the nearest neighbors algorithm, and it will tell you the description of the image, that where it is located into the world. So there are 6 million geo-tagged photos by about over 100,000 photographers around the world, and your dataset is marked with the geo-tagged location, that is the locations are marked on the global map. So this employs the scene mapping. The algorithm takes the input of an image and it maps with the training sets and assigns the labels to the country wise and the city wise. And the most near example is the labeled as output. So as you can see, the image of a building in the Paris is mapped to different cities, and the most nearest example will be marked as output. So here is another example. So this highlights the importance of data once again. So as you can see, as you increase the database size, there is larger chance that your first nearest neighbor will match the actual target. So you should employ certain techniques to improve on the data to improve the accuracy of your algorithm. So it also employs the techniques to complete the scene optimization. So as you can see, we have the image which was presented as an original image, and the authors provided the input by eliminating some parts of the image, and the image is again mapped to the nearest neighbors to reconstruct the output, which was equivalent to the almost equivalent to the original image, but with some modification because the algorithm also employed the certain techniques to context match. For example, here are the images. The original image is mapped with the context that it is a sea and it can contain the boats, and the same image is reconstructed to provide the context matching. So this concludes the discussion of the nearest neighbors algorithm, and we can find we found out that the algorithm is very simple to employ. However, there is a problem that it retains all the training data in the memory, and it can be slow in the testing because of the number of the calculations for each training example. And finding the nearest neighbor in the high dimensional is even more slower. Therefore, metrics are very important, and you should use the same metrics for all the examples. And it is a good baseline to build on your models or to check the accuracy of your models on any dataset. So this concludes our first part of the lecture, and in the second part we are going to employ same techniques, but this time we are going to explore the Tussian trees algorithm. So let's take the example of the emergency response whenever a patient visits an hospital, and how you or the machine learning can employ these assumptions to make decisions. So whenever the patient visits an emergency response, the physician or the person in charge asks for some triage information, that how the person is feeling, what's his age, and what he has eaten, and what are the physical symptoms such as pain or problem in the body. Based on this information, the physician may ask for some lab results or tests. After evaluating the test, the medical doctors make some comments about the um, diseases to explain or interrogate further about the diagnosis. And if the diagnosis requires further attention, it is referred to some special consultants which use the more diagnostic information to predict the actual um, disease or actual procedure for the patient, which is referred as the patient physician documentation. So as you can see, to make a decision, you have gone through a number of steps or the number of assumptions by different stakeholders or different feature vectors, or the input of different feature vectors directly impacted the outcome of the physician documentation. So here you should understand the importance of the initial triage information. So based on this information, can the doctor predict the infection? Because at the initial level, many crucial decisions are made about the patient care, because the amount of the pain in the patient's body or the distortion in the blood pressure or the sugar levels may significantly depict a problem in the patient. Therefore, the initial information analysis is very critical. So, based on these examples, you may or the physician may record the temperature of the patient, heart rate, and respiratory rates. So these are the normal values, and if these um, primary indicators are within the range, the doctor or the physician may have the uh, outlook that the patient has no significant problem. However, if these are not in the range, then there may be some underlying problem. But as you can observe that these are very simplified observation, because as to take the example, the heart rate is also dependent on the age, and you have to encounter these assumptions as well. So you may look for the other attributes of the patient, such as incorporation of the age, level of the pain and the acuity of the pain, the blood pressure level, and the oxygen saturation to make a better decision. So you plot this information using a decision tree, and based on the decisions using these division of the decision trees, you you propose the sampled output, and you predict that whether or not a patient has the infection or not. So that was the one of the complicated example. Here is a simple example. We want to classify the fruits as lemon and oranges. So we have two attributes, width and the height. So we can check that the first attribute is the width, and we have the parameter width greater than 6.5 centimeter. So if width is greater than 6.5, we check the height. So if height is greater than 9.5 centimeter, we classify it as lemon, or otherwise it is orange. On the other hand, if height is greater than 6.0 centimeter as well, we again classify it is as lemon, otherwise it is an orange. So we have the test example, and we check that the height of the test example is not greater than 6.5. So we check again, sorry, the width is not greater than 6.5. The height is again not greater than 6.0 centimeter. So we have the label example as orange. So again, in the decision trees algorithm, we have the decision tree boundary. The decision trees make prediction by recursively splitting the different attributes according to the tree structure. As you have seen, we have two attributes, and we recursively uh, divided these attributes to form a tree structure, as you can see, width and heights. As you can see, decision tree is a very simple but very powerful learning algorithm, and it is one of the most widely used learning algorithm in the critical competitions. Decision tree is an ordered set of tests, and for each test result you point to another test, and so on, or at the end you point to a leaf node with a class label. The decision tree is induced in a manner that maximizes its correctness on to the training data. But there are many decision trees, as with the many hypothesis assumptions for the same data. So how will you able to choose the best one? So we will discuss briefly about the tree selection criteria. Decision tree employs useful information theoretic concepts such as entropy, information gain, and mutual information, etc. So here is another example of image classification. Again, we use a decision tree to classify an image into an outdoor or indoor image, and we have different tests, and each test results in further tests until a leaf node, which results in a class label. So the first test checks that whether the top is blue, the top part of the image is blue, and we can see that it is blue. So in the true form, we check that is the image part of the bottom is blue, which is wrong here. So we have the false path, and resulting an outdoor label, classifying this image as an outdoor image. So what is the hypothesis here? Again, the hypothesis is the decision tree which correctly maps the input example to the output labels. However, here each internal node tests an attribute X, and each branch assigns an attribute value X of Y is equal to V. For example, we have another example to classify the example of cars, and we check or divide each test node on the base of attribute X, and in this case we have the attribute of cylinders, and each branch assigns an attribute value X of I is equal to V, as in this case we have 3, 4, 5, 6, 7, 8 as an attribute values. In the final or the terminating nodes, we have the leaf nodes, and each leaf assigns a class Y. So as in this case we have the class America, Asia, Europe, low, medium, high, etc. So to classify the input example X, you need to traverse the tree in some form to predict the output labeled Y, which you will encounter to the leaf node. And one of the significant benefit of the decision trees algorithm is that it is human interpretable. A human can provide the justifiable reason behind the prediction of an example. So decision trees can be used for the classification and regression task as well, and each path from the root to leaf defines a region of the input space. So you may have the different examples and the training labels to be the training example that fall into that input space, and for the classification task you may have the output values as discrete outputs in the form of labels. The leaf values output labels Y are typically set to the most common value in that specific input space or in the specific region of the or the part from the leaf from the root node to the leaf node. On the other hand, a regression tree provides the continuous output, and the leaf value output label Y or the output targeted value Y typically set to the mean value in that particular example input set or input space. However, in this lecture we will focus on the classification task. So what functions can be represented with the decision trees? So first of all, you can use the decision trees to model binary classification. However, decision trees can represent any function of input attributes. For Boolean function, path to leaf gives the truth table row. For example, as you can see, the first path false false gives the first row of the truth table. But it could require exponentially many nodes. However, on the other hand, if you have the discrete values, you can see that you have different values for each node, and you can traverse the path to find out a classification rule. So decision trees are quite expressive. However, if you have a discrete input, you have the discrete output. And in this case, decision trees can express any function into of the input attributes. For example, Boolean functions result in the truth table row, which are paths to the leaf. However, the representation or expressiveness of the continuous input and the continuous output is quite difficult, but it is manageable because decision trees can approximate any function arbitrarily closely to the predicted value. Trivially, there is a consistent decision tree for any training set, with one path to leave for each example, unless the function is non-deterministic in the example, but it probably won't generalize to new examples accurately. Therefore, learning decision trees is quite hard. Learning the simplest, even smallest decision trees is an NP-complete problem. So you resort to a old algorithm which is referred as the greedy heuristic to construct the decision tree, and you start the decision tree from an empty decision tree and then split the best attribute or the feature. So how can you find out the best attribute? So we will look into the explanation of finding the best attribute. And once you find out the best attribute, you recursively apply these steps to construct the decision tree. So here is an example. Again, we have the internal load question. What is the number of cylinders? And we have divided the cylinders to the different values. For example, 3, 4, 5, 6, 7, or 8. So as you can see, we have the cylinder 4, which we have classified as the best attribute because it correctly classifies a large amount of values, and we have the majority vote to assign this tree as the good predictor. So key idea in the greedy learning algorithm or the greedy recursion of the trees is to find out the number of examples classified by the each value. So you take the original dataset and then portion it or partition it according to the value of the attributes we split on. For example, if we take the previous example, we have the records in the cylinder 4, 5, 6, and 8. As you can see, records of the cylinder 4 are quite significantly greater than the rest of the others. So then, based on these cylinders and this cylinder, which had the most amount of the portion in the previous slide, we further divide on the next attribute. So in this case, we use the next attribute, which is the maker. So we divide the maker attribute and we had two further good predictors. So you use these values to recursively build the tree. So this is the further explanation of the same example or the full decision tree for this particular example. And as you can see, you use the cylinder 4 and cylinder 8 to divide, and then you use the maker Asia to further divide and maker Europe to further divide the tree, and so on. So as you have seen that you do not split when all the examples have the same label, as in this case you have the same labels of the bad examples, and you can not split when you run out of the question. For example, in this case you have the lost attribute of horsepower and you have no further division. So let's come back to the question, how will you choose the good attribute? So as in this example, would you prefer to split on x1 or x2? So as you can see, for the x1, we have divided the tree into the uh, two parts, as this is a binary problem, and we can see we have four correct classification in the true form and one correct classification in the false form. On the other hand, we have 3 and 2 correct classification if we divide the tree on the x2. So what is the good split here? And so do you use the first split or the second split? So it really depends on the accuracy gain, which split correctly classifies the maximum number of examples. So in our case, we can see that the first split is better than the second split. So instead of looking, we will use the techniques from the information theory. Idea is to count at least to define the probability distribution so we can measure the uncertainty of the each attribute. Before discussing the uncertainty, let's take the example of flipping two different coins. So as we flip the first coin, we have the sequence of the results. So we flipped the coin for 18 times and it returned 0 for 16 times and 1 for 2 times. Again we have another coin and we flipped the coin again and we have 8 results as 0 and 10 results as 1. So what do you think, which coin is more uncertain or which has the more uncertainty into the output and which is a fair coin? Exactly. The second coin is more fair and you have more chance that it will have the probability of 50% to predict as 0 or 1. Instead, the first coin is more unpredictable and it can have the greater uncertainty into the output value. So you may employ the certain um, techniques to cater the uncertainty, and entropy is one of the measures to find out the expected surprise or expected uncertainty. So to find out the entropy, you have the formula. To, to refer the entropy, we use the capital H symbol for the variable. So we have the formula minus summation x belongs to all occurrences, probability of x log 2 probability of x. So again we have two examples which have the 9 outcomes, and the first example shows that the outcome was 8 by 9 and 1 by 9 for 0 and 1 respectively. On the other hand, we had the fair output. So to quantify the uncertainty, we use the same formula and we put the values to find out the actual outcome. And in the first case, we have seen that the unexpected certainty or entropy in this case is 0.5. On the other hand, it is 0.99. So this measures the information content for each observations, and units represented here are the number of bits. So in terms of quantifying uncertainty, if the coin has the entropy equal to or near equal to 1, we can say that it is the fair output coin. Instead, if the entropy of the outcome is not close to the 1, we have the uncertainty of the quantifying. This graph shows the general relationship between the entropy and the probability. So as you can see, if the probability is near to 50%, that means there is slight deviation of chances, the probability or the entropy is equal to or close to 1. That means there is less chance of uncertainty. However, if you have lower values of entropy, there is great chance that the quantified values will have greater uncertainty. So, as I described in the previous slide, high entropy means variable has the uniform like distribution. That means it is more dense towards the center and it has equal probability for all the values. Therefore, it will result in a flat histogram and values sampled from this higher entropy are less predictable. However, if you have low entropy, the distribution of variable may have peaks and valleys in different form instead of a simple histogram. Histogram may have lows and highs as well, and values sampled from these uh, distributions are more predictable. So you can employ entropy to find out the uncertainty between different occurrences of events. So you can employ entropy to find out the joint distribution. As in this case, we have an example X which says which have the example data of raining and not raining and outputs of cloudiness. That means we check the occurrences of raining with the output of cloudiness. So we have 100 assumptions or 100 measurements of our variable and these are divided in the joint distribution. So we have 24 occurrences of raining when it is cloudy and 25 occurrences of cloudiness and no rain. Instead, we had one occurrence of raining without the clouds and 50 occurrences of not raining when there were no clouds. So you calculated the joint probability or joint distribution in the same manner of the entropy as the single variable. So you can find out the h of x comma y using the same summation, but this time you use the summation of joint distribution for both of the variable occurrences. So you employed all the occurrences of the variables and you find out the joint distribution to 1.56 bits. However, a joint distribution does not contribute significantly for the decision tree decisions. Therefore, you would like to find out the conditional entropy. So again, you have the same training data set and you would like to find out the entropy of cloudiness given that it is raining. So you will be using this dataset to find out the entropy of the cloudiness. So it is represented as the entropy of cloudiness given that the dataset is based on the examples of raining only. So you employed the same formula, but in this case you use the training set with the raining examples only and you find out the probability of the entropy of 0.24 bits. So this means that it has the highest chance of uncertainty based on the cloudiness and the raining. So again you calculate the expected conditional probability using the same formula as described in the previous. So based on these entropy calculations, you can find out certain observations which depict some useful properties. So the first observation is that the entropy is always non-negative. That means that entropy will be either zero or positive. Entropy also employ the chain rule. For example, if you find out the entropy of two variables or joint entropy x and y, and you find that the conditional entropy of any training data given x over y and the occurrences of the output y, which is equivalent to the reverse of that event with respect to the occurrences of the training data. So that means the entropy of the cloudiness given it is raining is equal to the entropy of raining given cloudiness. However, if x and y are independent, then x does not tell us anything about the y. So if two attributes are independent of each other and they do not contribute directly in the joint entropy, therefore the conditional entropy will be equivalent to the entropy of the outcome. However, the y tells us, the output tells us about everything of the output. That means if we only finding out the entropy of the variable with respect to all of the occurrences, the entropy will be equal to 0. So by knowing x, we can only decrease the uncertainty about the y, which is the assumed or the known fact. So as we know the examples, we can significantly decrease the uncertainty about. So entropy helps us to find out the information about the attribute. So decrease in the entropy reduces the uncertainty as per splitting. So how much information about the cloudiness do we get by discovering whether it is raining? So as you can see, we can get the information about the cloudiness based on the raining values. So the information gain is the criteria to specify the division of the attribute values in the decision trees. So information gain is represented as Ig, and it is for this case it is the information of the cloudiness based on the given input training example, as in this case it is the raining. So information gain is calculated as the entropy of the cloudiness minus the conditional entropy of the cloudiness given the training example of the raining. So we calculated both the values and the result is somewhat equivalent to 0.25 bits. So this result is called information gain in Y due to the known values of the training set X, or the mutual information of Y and X occurring together. So if the X is completely uninformative about Y, information gain is equal to 0. And if X is completely informative about the Y, the information gain will be equivalent to the entropy of the Y. Therefore, you can use this information gain to split the decision trees based on the attribute, and you will split the attribute based on the information gain value, which attribute has the higher value. However, the decision trees also suffer from the problem of the overfitting, because as the size of the training set, as the size of the trees or the number of nodes increases, there is an increase in the accuracy of the training data. But when you employ this same training, when you employ the test set on the same decision tree, you may observe some increased error rate and reduced accuracy. This is the typical representation of algorithm overfitting. That means you have overfitted the training data, therefore your algorithm is not performing accurately onto the test data. The result or the solution for these kind of problems is to choose a significantly smaller tree where you have the significant accuracy and the lower error rate. So to overcome the problem of overfitting in the decision trees, standard decision trees with the no learning bias are used. That means you do not make assumptions about the data, or you do not provide an additional value to compute your decision trees. So in this case, the training set is usually provide zero error if there is no label noise, and you must introduce some bias towards some simpler trees. Whenever you run the trees to a small or significantly smaller trees, you may introduce some learning bias to make assumptions to overcome the training error. And there are many strategies for picking simpler trees, and one of the strategy is to use the fixed depth trees. For example, you can put a restriction to have a tree with a maximum leaf or the node depth of 10 levels. Or you can also employ another technique to find out the fixed number of leaves, or you can employ the fixed number of leaves to have in a decision tree. The overfitting problem of the decision trees can also be mitigated by enforcing different ensemble method, such as employment of random forest. So we will discuss about the random forest of the decision trees or other algorithms in another lecture. The decision trees suffer mostly from the real valued input, because the real valued inputs have the uh, small portion of change with each value. So what should you do if you encounter with the real valued input? As in this case, for example, we take a real value. For model year, we have the infinite number of possible split values, or even if we have the finite number of possible split values, there are significantly larger values. Therefore, the real valued inputs are quite headache for the decision trees. So, for example, as you can see, one of the idea is to use one branch for each numeric value. However, this is a hopeless approach, as hypothesis with such high branching factor will shatter any dataset, and it is more likely to overfit again. Therefore, other techniques should also be employed. For example, you should replace the real values with the binary tree and split on attribute x at value t. And one branch you should have x less than t, and the other branch should have x greater than t. For example, in the previous example, we had the model year. We divided it as a binary tree, and we divided the year at 78, and we had one example, or the number of examples, as less than 78 and the other set as greater than 78, and then recursively uh, divided the year as less than 70 and greater than 70. So you can search through possible values of t, and however this also seems hard, but only a finite number of t's are important, so you can use this threshold split to mitigate the real valued problem. Or you can sort the data to according to the input examples into number of attribute values, and you can moreover use only splits between the examples from different classes. For example, if the for the same example you have different classes for the year 70 to 90, so you use only those split whereas different classes. So this leads us to the question that how will you classify the CN tree as a good tree? So, or what are the characteristics of a good Tussian tree? And several authors have proposed several strategies, and one of the famously known strategy is using Occam's razor. It finds the simplest hypothesis that fits the observations. It is a useful principle, but it is hard to formalize as it is very difficult to find the simplicity of the trees. However, it works well in the practical aspects, and if you want to read more about the Occam's razor or the definition of the useful trees, you can find out the relevant materials based on the author and the year. Or you can read the title paper, The Role of Occam's Razor in the Knowledge Discovery. But in the simple terms, we will desire small trees with informative nodes near to the root. We would like to have the decision trees which are easier to interpret and have lower danger of training data overfitting. We have discussed the problem of overfitting, and we will like to have the Trixian trees which reduces the overfitting problem. We will also like to have the decision tree which has the tendency to eliminate irrelevant and redundant attributes. And more importantly, we like to build the cheaper decision trees which are cheaper to use when the attribute values are expensive or difficult to obtain. So in short, we would like to have a decision tree that is not too small because we need to handle the important but possibly subtle distinctions in the data, and we will on the same time not like to have not too big decision trees because it will increase the computational cost and which will decrease the efficiency of the decisions, and it will avoid redundant and spurious attributes. When you compare the decision trees to the K and N, there are several positives. However, there are few limitations as well. So for the starters, the decision trees are very good to use when there are lots of attributes, but only few of those are important. So the decision trees are more better with the discrete attributes instead of K and N. The decision trees easily deal with the missing values, just treat as another value in the training set. Decision trees are more robust to scale of inputs instead of KNN, which significantly derails its performance with changing scales. Decision trees is faster at test time, and it is more importantly more interpretable. However, KNN has also some advantages over decision trees because the KNN has the fewer parameters or hyperparameters, and as you remember, there is only one hyperparameter in the nearest neighbor, which is the hyperparameter hyperparameter of calculating the distance between examples. However, in the decision trees, you have to control the number of leaf nodes, the depth of the uh, tree, and other relevant parameters. The KNN are able to handle attribute features that interact in complex ways, for example, pixels. But for the decision trees, it is very difficult to handle the features which are very complex. KNN can incorporate interesting distance measures, for example, shape, context, and these make typically better predictions in practice. So at the end of this lecture, I would suggest you to read the reading material which is uploaded onto the CMS, and there is a code file accompanied into the zip folder. So you can open the file into the Jupyter notebook, the setup you have created into by using the first lecture. And there are two examples, and the usage of these two algorithms is provided in that code file. So in the first task, I would like you to suggest you to practice with the k nearest neighbors example classifier. So you are given a dataset of handwritten digits called the MNIST dataset. So you try to build a classifier for MNIST dataset that achieves over 97% accuracy on that test set. So you use the k nearest neighbors classifier that works quite well for this task. You just need to find the good hyperparameter values. So you can try a grid search on the weights and the number of neighbors hyperparameters. For the second task, you should train up and fine-tune a decision tree by using the Make Moons dataset with 10,000 samples and a noise of 0.4 to generate the Moons dataset. Then use the train test split method to split the dataset into the training set and the test set. Again, using the grid search here with the cross validation grid search CV to find good parameter values for the decision tree classifier. Again, try various values for max, leaf, nodes in the decision trees. Train it on to the full training set with hyperparameters and measure your model's performance onto the test set. You should get about 85 to 87% of accuracy. If you have any problem running the code, feel free to ask me. If you want to read more about the topic, you can go through the selective topics of the chapter 3 and chapter 6 of Introduction to Machine Learning reference book. If you want to ask any other question, you can ask me through the designated mediums, or you can conduct a question and answer session on Microsoft Teams. Thank you very much for your time.